Hello, everyone. Thanks for joining. Let's wait a few more minutes for others, then we can start. Hey,
Yeah,
Pratyush,
how's it
feel free
going?
to good. Feel free to share your screen to see if it works.
Yeah, I'm just compiling some final changes from my slides, and as soon as Overleaf lets me, I'll do that.
No worries. No. Perfect. I think we can start slowly. Let me start with introducing Pratyush. So Pratyush has fairly recently finished his PhD in cryptography from John Hopkins, where I believe he focused on ZK SNARKs among other things. Um, I've been following his tweets around like security of a SNARK system and TEs and other various things, and like it has been like a source of like good nuggets and new understandings for me. So I invited him to share some of his insights with us, and today he's going to talk about security of FRI-based SNARKs. Looking forward to learn about this topic. Um, the
Awesome.
the floor
Thanks a
is
lot.
yours.
Awesome. Thanks a lot, Mo. I'll quickly get my slides up and then start. There we go. So let's see. Do you guys
Perfect.
see this in like slideshow mode? So you see the slides moving, right?
Yes.
Okay, awesome. So yeah, hi everyone, I'm Pratyush. I've been working on a variety of cryptography research and engineering problems in the last few years. Uh, a lot of the work has been in close collaboration with the Ethereum Foundation. Some of the results that I'm going to present today also were results of an Ethereum Foundation grant that funded my PhD. And now I'm building Eternus. We're working on trust infrastructure for the future of the internet. More on that later, but let's dive into some insights into the security risks of FRI-based SNARKs. There we go. Cool. So this talk has insights from two recent works. One of them was at ASIACRYPT last year, and the other one was at SCN this year. And this is joint work with a bunch of great co-authors. Alex Blog, who's just started a tenure track role at University of Illinois Chicago, Albert and Mihal from Nethermind, and John Katz at UMD, and Justin Taylor, who's at A16Z in Georgetown. Great. So yeah, so let's start with why FRI, right? So why is it important? Why should we care about it? So it's quite popular in the SNARK space. If you look at so this image is slightly old. I know L2B like moves every day by a lot. So this is just to show that 6 months ago, roughly, there were a bunch of protocols that were using FRI-based SNARKs at a conjectured security level. And over this talk, what I'll discuss is FRI security, what are the conjectures around it, and how much is the gap between our understanding of FRI security in the real world, the best known attacks, and the gap between the conjecture and the security we can actually prove today. Yeah, so there's a bunch of Flonk-like protocols that are used in many L2 projects, and they have like different amounts of conjecture security. And before these works, there was no formal Fiat-Shamir security analysis of FRI. The reason why this is important is Fiat-Shamir security of multi-round protocols is not something that you get out of the box. These protocols are described as multi-round interactions between a prover and a verifier. But in reality, we use the Fiat-Shamir heuristic to get randomness as if it were from the verifier using random oracles, which we model as hash functions. Now, the security of these protocols is then proven in the interactive format. So assuming that there is a verifier that is providing a high quality source of randomness, but then in the real world, we start using Fiat-Shamir, and then the security doesn't translate directly from interactive to non-interactive security. So these considerations have to be made when switching modes from interactive to non-interactive, and for FRI, such an analysis did not exist before. So in this work, in the ASIACRYPT work, we proved the Fiat-Shamir security of the FRI protocol, its batch FRI version. We introduced this notion called Delbecq correlated IOPs. More on this later, but we proved their Fiat-Shamir security as well. Intuitively, these are just protocols that use FRI as a subroutine. Then we formulate Delta correlated IOP, which captures many Planck-like protocols and prove their Fiat-Shamir security. Ultimately, we want to capture the security of SNARKs that use FRI as a subroutine. And a lot of SNARKs that people are using in practice today, including the ones that you see on the screen, do use FRI, like Plonky2, something that RISC-0, Deep FRI. And yeah, when we say Planck-like, we mean that these protocols are using FRI as a subroutine, and they have a permutation argument, which was popularized by Planck as a SNARK. Cool. And then in the end, most importantly, how does this impact concrete security of like FRI-based proof systems today? Right. So I'm just checking quickly. The animations are coming up, right? So you guys see a prover and verifier on the screen. Okay, awesome. Yeah, so I'll just do a quick run through of SNARKs in general, right? For SNARK protocols, we have a prover and a verifier. The prover is trying to prove to the verifier that a particular instance satisfies a relation, and the prover knows a witness for this fact, sends a proof to the verifier checks the proof, and accepts or rejects, right? And we have certain security properties. One of them is completeness, which is that if the relation and the witness is actually satisfied, then the resulting proof should be accepted by the verifier with probability 1. Then there's epsilon soundness, which means that if the prover actually doesn't know a witness such that the instance is in the language, then the probability of the verifier accepting should be very low. Then there's also a notion of knowledge soundness, which says that for all such instances and soundness methods, there exists an extractor where, given a valid instance and a proof, the extractor can get the witness out. Yeah, and then the other important notion, which is the reason why SNARKs became popular in the last decade, is succinctness. And this is described usually as the size of the proof being quite small, logarithmic, almost in the size of the instance and the witness. So what is the SNARK construction paradigm that we're going to discuss today? So one popular new construction paradigm that is being used in many protocols today is interactive oracle proofs. Interactive oracle proofs are a hybrid between probabilistically checkable proofs and interactive proofs. So what do they look like? You have a computationally unbounded prover that says that it knows an instance and a witness such that it satisfies a relation, and it sends an oracle to a verifier. The verifier then sends some randomness back. The prover sends another oracle, and this continues for R rounds. In the end, there's another phase where then all the oracles are received by the verifier. The verifier queries these oracles, does some computation, and accepts or rejects. The important thing here, why this is considered a hybrid between probabilistically checkable proofs and interactive proofs, is the following, right? In probabilistically checkable proofs, the prover just sends like one oracle, the verifier checks a bunch of things from the oracle and then accepts or rejects. In interactive proofs, there's multiple rounds of interaction, And this kind of combines both of these paradigms. Now, of course, to actually do this in the real world, the way we do this is replacing the oracles with Merkle trees, and the verifier queries are replaced with Merkle authentication paths. So every oracle is a huge Merkle tree and the root that the prover sends to the verifier. The verifier sends challenges back. The process continues. In the end, the verifier queries the oracle, and the answers are Merkle authentication paths for things that prover picked, just to show that this was indeed the thing that prover committed to. And then these authentication paths are checked by the verifier in terms of the consistency against the root, and then it outputs accept or reject. Yeah, and then you can combine with the Fiat-Shamir heuristic, you combine verifier challenges. You replace the verifier challenges with hash function calls, random oracle calls, and then that makes the whole process non-interactive, and the entire transcript can be put inside a proof that then can be checked by a verifier deterministically. So yeah, as I was saying, Fiat-Shamir transformations are not secure in general, even in their random oracle model. There are certain types of sequential and parallel repetitions of constant sound interactive protocols that are not secure. So this means that if you have protocols that have soundness, say 1/3, when you do one instance of the protocol, it's not. There are ways to combine it sequentially or parallelly that does not enhance soundness at all. In fact, it can even result in deterioration sometimes of the soundness. And so applying Fiat-Shamir to many-round protocols without formal security proofs has a high risk, right? Because most papers actually prove interactive security. Cool. So with this, yeah, you have a question?
Yeah, I was wondering if you can give us like a simple example where this parallel or sequential repetition doesn't help. Because like intuitively, if those instances are independent, you would assume it help, or like.
Right. Yeah, so let me think of an example quickly. So yeah, let's just take an example of a protocol where the soundness error is like 1/3. And so depending on the randomness chosen with probability 1/3, the prover can convince the verifier of something not being in the relation, like coming up with a proof for it. Now, if you repeat 2 instances of this sequentially, so you do 1 round of the protocol, right? And then right after that, you do another round with this maybe even like new randomness. What you can do is you start with something, and there's this paradigm called rewinding. I don't know if you guys have heard of it. In terms of non-interactive proofs, it's called rewinding because in some sense, the prover is like hashing and like producing the randomness. So when we say the prover rewinds, what it does, it starts from scratch again, picks something different, like one variable in the protocol that it can pick, it changes it so that the randomness changes. And then the prover gets to pick the randomness again. And that allows the prover to sort of like game the system. So now you start with something that has probability 1/3. The prover samples randomness such that it can convince the verifier of like an incorrect instance, like being in the relation. And then in the second round, again, the prover samples randomness again, rewinds. And so doing this sort of sequential approach actually did not help us at all in terms of improving the soundness of the protocol, because the probability of the prover sampling randomness doesn't really like help in this case. So it has to be combined in a more particular manner. Great. Okay, so let's talk about the FRI protocol. Stands for Fast Reed-Solomon Interactive Oracle Proofs of Proximity. So that's a mouthful. Let's break it down. So there are certain parameters that we have to care about. So FRI usually happens over like some finite field, particularly some multiplicative smooth subgroup of this field. And then we say that, okay, there's some degree bound. So we'll call it D0. And then what is the Reed-Solomon code here? The Reed-Solomon code is simply defined over the field, the multiplicative subgroup, and a degree bound. And it says that this is basically a list of polynomials that are degree up to d0 in this space where the variables are coming from the smooth multiplicative subgroup. There are certain other parameters, such as the rate of the Reed-Solomon code, which is defined accordingly using the degree bound and the size of the multiplicative subgroup. There are proximity parameters that define an idea of like the distance between polynomials. And we'll talk about these things as we go through different theorems here. Yeah. In general, yeah, what FRI proves is that given a function, G0, if it's like delta close to some Reed-Solomon code of like appropriate degree. So that's what we're checking here. We're checking proximity of polynomials in terms of the Reed-Solomon code space. So you check if a polynomial is like delta close to an appropriate polynomial of a certain degree. Yeah, so now let's talk about how do you prove like soundness of such an object. We'll cover more details in terms of exactly how FRI works, but I wanted to cover a soundness definition that we utilize in terms of completing this proof. So there's this notion called round by round soundness, and it also has an extractor version that's called round by round knowledge soundness. The idea of RBR soundness is that, let's say there is an instance that's not like in the language, then the protocol should be doomed, which means that a prover should not be able to convince the verifier that it's in the language. So now no matter what the prover does, the protocol should forever remain doomed in the multi-round protocol. So more formally, this says that you have a protocol pi for language L, and it has round by round soundness error epsilon if there is a doom set of partial transcripts. So transcripts are interactions during the proving conversation, but they're perhaps not complete yet. So if the instance is not in the language, then the protocol, the transcript sort of starts in the doom stage. And then for all complete transcripts, if you end up in a doom state, then the verifier rejects. And let's say you have a partial transcript and you have the verifier like samples more randomness, then the probability with which the prover sort of escapes the doom set is less than epsilon. So as long as your instance is not in the language, you start in the doom state, there's very low probability during the protocol for the prover to actually escape the doom state. And then in the end, if you're in the doom state, then the verifier always rejects. So it sort of is modeling the fact that over different rounds in the protocol, the prover cannot do anything massively advantageous to escape the verifier knowing that the prover, a malicious prover, is trying to cheat. Yeah, and then we use some existing results that are very fundamental. BCS16 and CMS19 are these two papers, and they say that if you can indeed prove round by round soundness of a multi-round protocol, then it does imply Fiat-Shamir security. The error rates are correlated in terms of the random oracle model. So you have an adversary that can make Q queries to the random oracle, and you have a kappa bit output from the random oracle. So this is a result that we then use. So what we do is we first prove round by round soundness of FRI, and then we instantiate using BCS16 to show how much security it has when you use it non-interactively. Yeah, so in terms of the main results of the paper, theorem 1 basically gives us round by round knowledge soundness. So this also comes in terms of like an extractor, but the round by round soundness error is this epsilon value, which is comes from the maxima of these two particular values, one coming from how folding in FRI happens that we'll discuss, and the other one coming from randomness that the verifier uses. And yeah, the same result holds for batch FRI, and yeah, some other details here. Before this, only interactive soundness of FRI was known in terms of the epsilon terms that relate folding, verifier randomness choice, things like that. And our run by round soundness error is related to the error bounds before, but we take the interactive world and bring it to the non-interactive world. Then we have the notion of delta correlated IOPs, which is different prover messages that are sent. We have certain requirements that are useful for FRI here. So you have delta correlated IOPs, which means that the prover messages are in the Reed-Solomon code space and are delta close to a Reed-Solomon code. So, I mean, at a high level, you can think of it as like a Hamming distance between like different polynomials. Yeah, and the verifier has access to oracles where it can check like how close two particular polynomials are. And this kind of gives us a new paradigm for SNARK design. So you have, let's say we can construct a round by round knowledge sound IOP. When it's zero correlated, means that, you know, it's exactly the same polynomial roughly. And then you can combine it to a protocol that allows using delta correlated IOPs, so things that are slightly further away. And then you can use the IOP that we have for delta correlation in our paper, along with theorem 2 that takes you from delta correlated IOPs to round by round sound IOPs. And then using the BCS16 transformation, this can be converted to a SNARK. Yeah, so in this paper at a high level, we have these results. So we present a delta correlated IOP called OPONKI, and it captures multiple Plonk-like protocols that use FRI as a subroutine. We then prove the round by round soundness for this particular delta correlated IOP, and then this can be then used to prove round by round soundness of real world protocols like RISC-0. And then each SNARK has also been independently proven to be round by round sound in related work. So for the remainder of the talk, I'll give like a good overview of how FRI works. We'll discuss some details of the round by round soundness proof, and then we'll dive into some things which are probably the most interesting to the crowd here, which is what is the real world security of FRI today, different variants and their soundness. I'll pause here if there are questions. Great. All right, so let's look at the FRI protocol. The FRI protocol, at a high level, you can imagine there is this large domain over which you have a polynomial, and what you're trying to prove to verify that this polynomial is of degree d, right? And there are some simple ways you can do this. Of course, you can just send the polynomial to the verifier, and then the verifier can check what the degree is, right? What we're trying to do is do much less work in terms of what the verifier has to do to check such a proof, right? So we start with a sort of a large domain where the polynomial is supposedly degree d, and then the evaluation of this polynomial over the domain is sent to the verifier. The verifier is not checking the whole thing. Otherwise, you know, it'll be the same as like sending the entire polynomial itself. What the verifier does is, okay, it says, okay, you sent me this oracle, great. Now here's some randomness that you can use to reduce the size of the polynomial in half. So that is the folding approach. What it does is it reduces degree by half. And exactly how it works is, imagine a large polynomial evaluated over a domain. And what it does is, in some sense, it takes the left half and the right half, uses some randomness, and folds it. And so this reduces the size of the polynomial by half. And then you continuously recurse on this approach. And what happens in logarithmic number of rounds in terms of the degree of the polynomial, you end up with a constant value if you keep folding things. So here's some more details on the folding phase. So in a particular round I, the prover sends a folded polynomial. The verifier sends some more randomness. And the next fold, what it does is it combines basically the even half of the polynomial and the odd half of the polynomial. So think of any degree D polynomial, right? So we'll have a bunch of coefficients for, x, x squared, x cubed, x to the 4, things like that. The way this is done is you can break any polynomial into two parts. So you can take all the even parts, the even powers, and then you can take all the odd powers. And then you can write the odd powers. So x, x cubed, x to the 5, you can write them as x times a bunch of even powers. And so this is the sort of breaking of the polynomial into two halves and using randomness to combine them. And then you recurse on these to reduce the size of the polynomial over a logarithmic in degree many folds. And yeah, ultimately you get something like this. The verifier has logarithmic in degree many sort of oracles that the prover committed to. And then the verifier can check consistency between the folds because we took the two parts of the polynomial, used randomness to fold them. Each sort of oracle that has been sent by the prover is related in a particular manner. So you can perform a consistency check to see if the prover actually folded the thing correctly, right? And so this is the consistency check part. So it's called the query phase, where the verifier checks that, okay, you sent me a bunch of these oracles, which were supposedly folded using the randomness I sent. So let me actually check that this works. And then the verifier repeats this process L times to increase its confidence and improve the soundness of the protocol. Yeah. So this is some of the details on the consistency check. I'll skip this for now. Yeah. So there's two phases in FRI then. One phase where the prover consistently folds the polynomial to make it smaller and smaller. And then the verifier checks the oracles that the prover sent in terms of the polynomial to check if the folding was indeed done correctly. And think about what we accomplished here, right? So the verifier has some constant number of checks that it's performing at each of the FRI fold levels. And so how many FRI fold levels there are, they're logarithmic in degree many folds, right? And so what we accomplished is that there's a prover and a verifier. The prover has a degree D polynomial. The verifier only did logarithmic in the degree work and was able to check with high probability that this polynomial is only degree D. So that's like the magic of the FRI protocol. Doing something like this was not possible in the past. Yeah, and then the two sources of soundness errors we'll see come from the verifier choice of randomness when folding the polynomials. And then the second source of sort of soundness error comes from the consistency check the verifier performs. Of course, these are oracles, so it's not like the verifier is going to check every spot in the oracle to see if there are issues. The verifier checks these spots probabilistically, so there is some scope of soundness error if there is a bad spot in the oracle that the verifier does not check. Great. So now we'll come to this notion of round by round soundness, which was we talked about the protocol transcript being doomed. So if you have a cheating prover, it starts with a doomed approach and then a very low probability of escaping being caught by a verifier. And so we'll see how this works for FRI. So you have in the beginning, you start with this domain L0, and let's say you have a polynomial that's actually not degree D, right? It's degree higher than that. And then, so you will be delta far away for like a particular proximity parameter. You will be far from the Reed-Solomon code because this is only for polynomials up to degree D. And so the protocol will start in the doom state. This prover is malicious. The prover would send this oracle. The verifier will send back randomness. So now G0 is what we started with. G1 would be the next sort of polynomial oracle that the prover provides. And now, if now somehow after folding the folded polynomial G1 is somehow delta close to the Reed-Solomon code, then post this point, the prover can behave honestly and fold the verifier. So this is the thing we need to account for. If you start in like a bad protocol state, so it's not actually degree D, and after that you do some folding and it becomes a low degree as it was supposed to be. If the prover was had like the right polynomial, then we're in trouble. So what is the case in which something like this can happen? And some older work on proximity parameters for FRI do have some probabilities around this in terms of when this can happen. So this is over the choice of a bad randomness. So you pick some alpha 0 value, and supposedly there's a probability with which you can pick a bad alpha such that this can happen, where you take a high degree polynomial, but you fold it so that maybe the high degree terms disappear and it becomes low degree. So yeah, what happens in the soundness of the folding phase here? So in a particular round I, let's say again you're in like a doom state, the verifier picks some randomness that's bad. The protocol is doomed if and only if the folding is not a correct folding. So perhaps the prover is like, hey, like I have a polynomial that's high degree. Let me just cheat in terms of designing the oracle. I will take this randomness and I will switch out a bunch of oracle entries to make it seem like the polynomial is actually low degree. And yeah, if this actually happens, that's like a cheating thing that will be caught in the consistency checks. And then the second probability is that the verifier picks bad randomness so that the fold actually becomes favorable. So we use similar arguments from the proximity parameters paper that talk about the probability of alpha I being bad in terms of the randomness for folding. So yeah, this was the folding phase. And then what happens in the query phase? So in the query phase, now the verifier is doing consistency checks for all the prover work. So the prover in the end sends this oracle, which should just be a constant, right? After logarithmic in degree many folds, the protocol is not doomed, and so the verifier checks only if the final value it gets is a constant that it expects. All verifier checks pass in terms of the consistency. So there were basically L different rounds over here for consistency checks. And if you assume that the polynomials are delta far from a low degree polynomial, in one consistency check, the verifier sort of not finding issues, the probability for that is 1 minus delta. So there's delta fraction of bad pieces and the verifier does not see them. The probability for that is 1 minus delta. You repeat this L times over the query phase and you get this probability 1 minus delta to the L. Yeah, so these are sort of the two terms. So 1 minus delta to the L, and then the term over here for the randomness being bad coming from, m plus 1/2 times size of the subgroup squared over the size of the field and the proximity parameter. Yeah, so these are the two sources of soundness errors, this one here and the 1 minus delta term from the query phase. So this was some high level intuition for, how we approximate in every round what is the probability of a malicious prover convincing the verifier. And this gives us the round by round knowledge soundness, round by round soundness, and then we use this to sort of build an extractor. I won't go into the details for that. And we additionally proved that the round by round knowledge error is equivalent to the round by round soundness error. So what is the intuition for round by round knowledge? It says that if there's a cheating prover that can leave the doom state, then you can extract a valid witness from the transcript that is not actually doomed. Yeah, I'll take the question.
It might be a stupid question, but I'm wondering, like, so even when we were like proving soundness or like analyzing soundness of like FRI in the Oracle model, we should have accounted for all these like failures of tests and like soundness errors. I'm wondering, like, specifically how we could account for like additional like soundness error that's caused by Fiat-Shamir. Like, I don't have like any intuition like how we can like account for that. Like, But is there like any concrete attack that we can think of that is possible now? That, I mean, obviously you can
Yeah.
try different
No, no.
randomnesses, but like yeah, I mean, what kind of techniques we have like to like calculate this additional advantage of the malicious prover?
Right. I mean, that's a great question. So in general, if we start with like just the interactive security of the protocol, right? So FRI was proposed as this like, you know, proof of proximity protocol, and then the security was proven in terms of the interactions. So the verifier actually picking randomness, they had a bunch of theorems that related these ideas, which was like, okay, like if you are as a prover, you get some randomness from the verifier to fold stuff, what is the probability with which like these things are bad? And then you have the query phase, and then in the query phase you have some probability with which, you know, the verifier misses checking like the bad parts of it. And yeah, that's the interactive security of it. Then the question is, okay, like we have the interactive security of the protocol, then we have the Fiat-Shamir heuristic. Can we use it directly to just say that the interactive security is the same as the non-interactive security? Such results are not available, and the reason for that is like in many protocols there are like counterexamples, similar to the example I was using earlier, where if the randomness is actually coming from a verifier, then the prover cannot really like rewind in some sense in the real world. It's an interactive protocol. The verifier gives you some randomness. You just have to use it, right? And then the security holds. In the real world, like when you start using the Fiat-Shamir heuristic, then the prover can start doing like a lot of things with the randomness, and which is why we have these particular soundness notions, and we say like, okay, like if you can say things very concretely about every single round of the protocol, what is the probability of the prover doing bad things, then you can compile this protocol using Fiat-Shamir, and then it's a convincing mathematical argument. The other problem is that it's hard to enumerate over all possible malicious prover strategies, right? Which is why we use established theorems to say things. What I mean by that is, let's say there's a protocol that's secure in the interactive world, then you go into the non-interactive world. Okay, the prover can do a lot of things here, and in most cases, it's like hard to iterate over all the possible cases and say like, okay, the prover cannot do anything at all. So instead, what we do is we say, imagine that we talk about like the errors in like one round at a time, and then we have this notion of like round by round soundness, and then we say, okay, cool, if the protocol does have round by round soundness and you use Fiat-Shamir properly, then we know the number of malicious prover strategies. Now we can like kind of like iterate over them, and then we can actually prove theorems. Yeah.
Thanks a lot for that explanation. Now I understand what's the purpose of round by round like soundness
Awesome.
definition.
Great. Yeah. Yeah, it's just without it, it's like hard to formalize overall malicious prover strategies and have like a theorem type statement that we can prove. Yeah, cool. Okay, yeah, and then FRI also has a bunch of variants that people have used in practice. So there's several optimizations of it. So there's something called dash FRI, because in the real world protocols, people take a bunch of polynomials, combine them, and like run FRI over that. So that's dash FRI. Then there's larger FRI folds. So instead of folding things in two, maybe you take like two pieces of randomness and you fold, you know, the three different pieces of a polynomial into just 1/3 of it. Or, you know, you take like C different parts of the polynomial and fold it to a 1C sized, 1/C sized polynomial. That's another optimization people use. And the other one is early folding phase termination, which means that, okay, you start with a polynomial that's degree D, maybe you don't fold it like all the way down and you just stop like when it hits like a degree 10 polynomial, at which point the prover just sends the polynomial itself to the verifier. These are some different optimizations that are used in the real world. And so in this paper, we also talk about, how does the round by round soundness is affected by these FRI variants. I won't go into too many details, but I think similar ideas apply. If you're batching a bunch of polynomials, you should sample randomness that's like independent. If you sample one point in randomness and then just take, r square, r cube as the other points of randomness, then bad things happen because the randomness is not independent. So these details can be found in the paper. Now let's get into the more interesting part of this analysis, which is the second paper. So how does this affect like real world parameters today, right? So we have some results that, I talked about theorem 1 that allows us to calculate how much error there is. So in terms of bits of security, how much work would a malicious prover have to do to come up with a valid proof for an incorrect statement. And we do this by doing this bits of security based analysis. So what this roughly says is, okay, you have this proof system that you use in the random oracle model. It has a particular soundness error that we know. Then it has lambda bits of security against certain adversaries that can make Q random oracle queries. So what this does is it says that, okay, you have this protocol that you combined, you have this epsilon round by round soundness error, and if you have a malicious prover that can make Q queries to the random oracle, then you have lambda bits of security, and then we can crunch these numbers. So we put in the real world calculations and we crunch these numbers. And so we can analyze the bits of security. So we put in the numbers for all the protocols. So what would be the epsilon value based on our calculation? We assume how many sort of hash function calls provers can make today based on, of course, it's a cost thing. Yeah, so if a malicious prover is really motivated, the protocol is less secure against them, of course, right? So based on this, so we talk about real world protocols. So the theorem 1 that I talked about gives us provable round by round soundness for FRI, but people are running, they're setting their parameters not according to the provable numbers, but there are certain aggressive conjectures about interactive FRI, and that is what people are using to set their parameters. What are these conjectures saying? Well, what these conjectures say is that whatever best possible attacks are known against FRI, so whatever malicious strategies are known today, they're saying that these strategies are optimal and no prover can do better than this, right? So there is, so we say that in the provable world, we say that the malicious prover can achieve like certain amount of security, and then in the let me start with this explanation again. So you see these two numbers that we talked about, right? So in terms of the soundness error, the first term and the second term, the first term coming from what is the probability with which you get a bad fold, and the second term coming from what is the probability with which the verifier does not consistency check on that points, right? So these numbers are just massively different. In terms of the first part, it's 1 over the size of the field. For in theorem 1, this was it was like size of the subgroup, so L0 squared over the size of the field, right? So the error is like much higher that we can prove things for, and this conjecture just does exist. Like people say that, okay, no prover will be able to do randomness sampling in a way such that it can like use a malicious strategy to attack the protocol. And this conjecture is slightly arbitrary. It just says that we know like an attack strategy today, and then it's making a bet that no one will be able to find a better attack strategy. And for now, this is an arbitrary claim. It is possible that this turns out to be true, or it's also possible that someone finds a better attack in terms of a malicious prover strategy. So if you look at the protocols deployed in the real world today, you have different amounts of conjecture security. So they set a 100-bit target, and they crunch their numbers and set their parameters so that in the conjecture world, they have 80 bits or 96 bits or 100 bits of conjecture security. And why do they do this? The reason is, if you use the conjecture security numbers, then you have to sort of do less number of queries in terms of the query phase of the protocol, in terms of, so this reduces prover costs because the prover doesn't have to open as many like Merkle tree authentication paths. The verifier doesn't have to check as many Merkle tree authentication paths. All of this reduces prover costs, verifier costs, and prover sizes, the proof sizes. If you were to use the numbers that we provide in the provable landscape versus the conjectured landscape, there's a 2x cost difference. And so these protocols, they decide that, okay, we believe that no one will find a better attack on FRI, and hence why we just set our numbers accordingly. So what is the real world impact of this? This means that they're saying if there's a protocol, FRI-based protocol, that has 100 bits of interactive security, you directly get 100 bits of non-interactive security. Based on our analysis, when we put down these numbers, what we see is there's a huge gap in terms of the actual non-interactive security of the protocol, which means that the green numbers and the red numbers you see on the screen is a honeypot. So if there's a really motivated attacker that has immense knowledge of coding theory and things like that, then you can, the range over here is talking about different deployed protocols today. So some have more non-interactive security, some have less. So the gap ranges between mild and huge. So we give explicit trade-offs between, adversarial hashing power, the success probability of an attack, and then we use our results to give concrete parameters. So if you are someone who is more conservative in terms of how you want to deal with cryptography, and maybe user funds are at stake, or maybe depending on the use case, you don't want the malicious prover to convince a verifier. Maybe you're a ZK-based L2 and you don't want people to be spending money that they don't have, then it makes sense to be a bit more careful. We provide a simple tool in the second paper that allows you to calculate your FRI parameters. And so you can plug in the size of your field, all of these details, and it'll tell you exactly how many queries you should do in the query phase, things like that. So this is a quick sort of bird's eye view of the things we do today. The full version of these papers are available here, and I will share my screen in terms of what does the table look like for the different protocols today. Thanks, everyone.
Thanks a lot, Pratyush. That was a very condensed, informative, great talk. It's
Awesome.
it's indeed a little bit more like on a cryptography side than what this crowd is used to, but it was great nevertheless.
Great. It's hard for me sometimes to clock exactly who will be the people who are attending it, but hopefully everyone got a little bit of something. This is the table, or when you actually do the analysis for these proof systems that are deployed today. What is the gap between the provable security numbers that come from our theorem versus the conjectured security that just assumes that better attacks won't be found? So the gaps do indeed end up being huge. And we did, this is not we're not proposing a better attack. We're just saying, look, it's possible that either people find a better attack and then your protocols are at risk, or someone needs to go in and prove the bounds to be tighter, and which would show that better attacks indeed do not exist. And we informed all the relevant teams of this result before we made this work public. That's it from my side. So one more thing I wanted to add is, how do you think about this like conjecture versus you have these cryptographic assumptions, like the discrete log problem is hard. Like, what is the difference between the conjecture and like cryptographic assumptions? So one sort of analogy I like to use is when we talk about cryptography or cryptographic assumptions, it's always about a bounded prover, right? So it says a bounded prover or a bounded like adversary. So we know that the discrete log problem can be broken. So if you have g to the x, you can get x if you have unlimited computational power. We just say that, okay, if you're an adversary that has, you know, real world capabilities, then to the best of our knowledge, like this particular attack is secure against bounded adversaries. In the information and theoretic landscape, what you're saying is something different, where you're saying that even if your prover or the malicious prover or the adversary here is completely unbounded, even then my conjecture holds. So no better attack strategy can be found. And this is like hard to be convinced by because there's no way for anyone to enumerate over all possible attack strategies of an unbounded adversary, right? So that just ends up being slightly more unreasonable. Yeah. And that's like a bit more subjective in terms of what's reasonable, what's not reasonable. But that's sort of my intuition on it.
I have a quick question about like the final table.
Yeah.
If you want to like give one or two like main reasons why the reduction in. So I have two questions actually. The first one is, do you think like given like that you did the analysis for like the provable analysis, do you think there are parts of the proof that are very untied and could be easily like improved, or your feeling is like we need new techniques to kind of improve the bounds? And the second question is, what is the major contributor to like this wide difference in reduction of like bit security? Is it like a field size, or is it like something non-trivial?
Yeah, so there's a couple of main things. So I'll answer the second question first. So the reason why this differs a lot for different protocols, the gap between conjectured and provable security is just around how aggressively they set their parameters, right? And the sort of how aggressively here is implied by in the query phase when the verifier checks different parts of the Merkle trees, how many different pieces of the Merkle tree does the verifier check? Of course, if you check more, then you have better security, but the proof size also increases, verifier work also increases. So some protocols are more aggressive than others and say like, okay, we will only check 10 points on the Merkle tree and we find that to be satisfactory enough. Of course, field size also plays a role in this, like people use different fields depending on the rest of their protocol. And yeah, the first part in terms of the tightness. So we try to do it kind of both ways, right? So as far as I know, there's no simple way to make the provable analysis tighter just yet. I think what you can perhaps do is try to mount like better attacks, like that might be possible. I mean, if at this point it's like hard to be like sure. Maybe there's someone who comes in, looks at our analysis, and then figures out a way to make things like tighter, and the gap between the conjecture and the provable security reduces. But it's also possible that someone finds a more clever way to extract nearby Reed-Solomon code points, and then they would have like a faster, more efficient way to attack FRI. Yeah, hopefully that helps.
That was great. Thank you. Any questions from the audience? If not, let's thank Pratyush once again. Thanks a lot, everyone, for coming and staying until the end of the talk. See you all next week. Thank you, Pratyush.
Great. Thanks, everyone.
Thanks so much.